Ladies and gentlemen, good afternoon. I'd like to introduce the Air Force component of our lightning talks. To kick it off, we have Samantha Borney, and her topic will be radiochemistry, molybdenum.
Hello, my name is Samantha Borney. I graduated from Texas A&M with a BS in chemistry in 2018. My sponsor facility is the Shambron Radiochemistry Lab under the Air Force Technical Application Center, which is more commonly known as AFTAC. Today, I will be telling you about my work in radiochemistry and specifically with molybdenum-99. AFTAC is in charge of the US's international nuclear treaty monitoring. This goal is accomplished through observing weather patterns to investigating seismic activity. And in my lab, we perform particle analysis on both ground and air samples, looking for specific fingerprint-like radioactivity. As you can see, there are many DoD applications involved in this work, such as the analysis of environmental samples. But one of the main applications is in supporting the nation's chemical, biological, radiological, and nuclear defenses. With that, here's a peek at some of the chemistry my lab performs. One of the main tasks is the digestion of those air and ground samples with a very hot oven for 25 hours and with some very strong acids to create a homogeneous solution. One of my coworkers likes to describe it like making a smoothie. You blend all the fruits together till it is one consistency. But instead of fruit, we have radioactive elements. We then perform various separation and purification techniques in order to pull out each element individually. You can see the list on the right of the elements we currently analyze for. Although, in an ideal world, we would be able to analyze every element on the periodic table. This graph shows the fission chain yield distribution of nuclear event with various starting materials. Most of the elements on this list are located near the two humps where the yields are the highest. Specifically, I work with molybdenum, barium, and strontium, and I will actually be learning cadmium chemistry later this summer. One of the most important ones I work with is Moly-99. I will be discussing the purification techniques, the decay scheme, and why this element is so important. Some common challenges we are working on with this chemistry specifically is iron, which is just everywhere, but tends to follow our Moly chemistry the most. The 6 different oxidation states of Moly that present its own unique issues, and the volatility of our final product, Moly trioxide. Moly chemistry is one of our longer and more challenging chemistries, though our Zerk chemistry does like to give it a run for its money. In this chemistry, we hit on many very common chemistry purification techniques, starting with a pretty intense flaming with sulfuric acid and bromine water to control the oxidation state of Moly. We also have many acid-based scavenging steps that we use specifically to remove iron from the solution. The bottom right picture shows how large our iron pellet can be sometimes. This pellet can easily trap Moly unless we clean it very well. One of the most finicky parts of the Moly process is the column separation. It is very temperature sensitive and can be slow going with salts forming and completely stopping the flow of the column. On a good day, this process can take about 2.5 hours. But on a bad day, it has taken me over 5 hours to get the chemistry to work again. We then precipitate out Moly in an hour-long ice bath and then transfer it to an oven for over 3 hours. Now, this oven step is one of the most crucial steps. This is the point where we are removing the daughter decay product, technetium-99 metastable. This is how we get a time zero for our beta counter in order to accurately calculate how much technetium-99 ingrowth happens so it can be removed from the final spectra. This is the point where if the ovens aren't set right, the volatility of Moly trioxide is an issue and could be burned off. While most of what I have discussed so far is pretty normal bench chemistry, there are some differences we have to keep in mind. One of the biggest ones is the time constraints we have. We are always racing the clock with our samples. For example, the half-life of Moly is almost 66 hours. This means that half of all of the material we have to work with will be gone in a little under 3 days. And with a lot of our chemistry, we like to stay within 5 half-lives. That means in under 2 weeks, there will be such a small amount of Moly left that it could possibly be under our detection limits or at least out of our comfort zone. Now, this might seem like plenty of time, but you have to remember we aren't creating the samples. This means we must also allocate shipping times for the sample to reach us. On a good week, this typically means we get the sample in 4 days. We now have 10 days left. But first, we have to digest the sample, which minimally takes 2 days to reach the portion where Molly will come off. We now have 8 days left. The chemistry itself takes at least 2 days as well. Now, any delays in shipping, any issues with the sample at the front end, throw a weekend and potentially a holiday in the mix, and we could be scrambling for time. Another difference is not only are we protecting ourselves from the sample, we're also dealing with such low levels of radioactivity that we have even more rules and guidelines on protecting the sample from the chemist. We aren't clean room level strict, but only barely. I also promised an explanation of why Moly-99 was so important to our work. The main reason is that Moly-99 is used as our reference isotope for the rest of the elements we analyze. Basically, in order to have numbers that are comparable, we compare everything to Moly-99. Moly was chosen because, first, it is one of those peak elements with a relatively high fission yield of about 6%. It is also roughly the same percentage regardless of the starting material, making it a very consistent element to analyze for. Moly is also fairly easy to measure, as we can count it both by gamma and by beta. And while it has a simple decay chain, it also has that very effective way of removing the daughter product, technetium-99 meta, with that oven step discussed earlier. Hopefully you've enjoyed my presentation on the radiochemistry of Moly-99. In all honesty, I'm incredibly grateful to the SMART program. Not only was my professional education sponsored by them, I was able to go into a field that I never would have dreamed possible. Unlike most of my fellow graduates, I didn't have a fruitless and frustrating job search after graduation. I knew where I was going and what I was going to be doing. I even knew some of my future coworkers already from my summer internships. There have also been many volunteer opportunities in my community to help teach and promote the STEM field to kids, and it has been so much fun to share my love and passion for science with them. This has been a great journey made possible by SMART that will continue throughout my career, whether with AFTAC or wherever my next steps may lead me.
Thank you, Samantha. Next up will be Daniel Enderich, and his topic will be high power microwaves for antiviral applications.
Hello, my name is Daniel Enderich, and today I'm going to be talking to you about high power microwaves for antiviral applications. But first, I'd like to tell you a little bit about myself. I grew up near Detroit, Michigan, and went to school for my bachelor's degree at Michigan State University, where I double majored in physics and mathematics. When I earned that degree in 2011, I joined the University of Wisconsin at Madison to study physics with a minor in electrical and computer engineering. In 2011, I applied for the SMART Scholarship, and in 2012, I was awarded it. And so for the next couple of years, I participated in internships at Kirtland Air Force Base while doing my PhD research. When I earned my PhD in 2018, I joined the Directed Energy Directorate at Kirtland Air Force Base, the Air Force Research Lab located in Albuquerque, New Mexico. So now a little bit about my technical expertise and some of the DoD applications that I apply it to. For the most part, I work on high power electromagnetics. More specifically, I develop high power microwave systems and charged particle beam systems. These systems help the DoD carry out its missions. There are a couple different applications that I'll highlight here, but there are many others. For example, we use these systems for counter electronics. We also pursue counter small unmanned aerial systems, or more colloquially, drones. Viral inactivation, that's something that I'm going to be talking a little bit more about in this talk. And then finally, port of entry inspections. On the left-hand side there, you can see a picture of the Tactical High Power Operational Responder, or THOR system. This is a system that my division has developed to counter the increasing threat due to drones on the battlefield and forward operating bases. Now, I'm going to talk a little bit more about the Viral Inactivation by Directed Energy Radiation, or VIDER project. This was a project that our division started last year as a response to the COVID-19 pandemic. As most people will know, the pandemic has cost the lives of more than 500,000 Americans and 3 million people worldwide. This is as of April 2021. The illness and the attrition that this pandemic causes really impacts the DoD's readiness. And so it's a very high importance that the DoD come up with a way of mitigating this pandemic and fighting back against it. In order to do that, we first need to know how the disease spreads. I'm sure most people know The illness is caused by the SARS-CoV-2 coronavirus, and this is spread primarily by droplets in the air that are breathed out by infected people. The virus piggybacks on those droplets. Uninfected people will breathe them in, and then the virus gets a toehold and the person becomes infected. So last year we started asking ourselves, what if it were possible to kill the virus in the air cheaply, rapidly, and unobtrusively? We want to do this effectively, but also without impacting people's day-to-day lives more than we have to. So to that end, we started looking through the literature to find out what research had been done before. And it turned out that initial research had been done on inactivating viruses with microwaves. This initial research typically focused on S-band from 2 to 4 gigahertz, and they used higher average power, lower peak power RF systems, namely industrial microwave ovens. In this research, it wasn't always clear what the exact kill mechanism was. Two have been proposed. There's the electromechanical, which is highlighted, demonstrated in the upper right-hand corner. And in this mechanism, what's effectively happening is the virus is being exposed to a rapidly oscillating electric field, and it responds by stretching and contracting. And if you do this hard enough, then eventually the virus splits apart and you no longer have an effective virus. The other kill mechanism is the thermal kill mechanism. This is the same as boiling water in order to sterilize it and make it safe for consumption. You're effectively transmitting the energy from the electromagnetic radiation into the virus, and that causes it to die. And once that's happened, it's no longer capable of causing disease in people. So to verify this initial research that showed that viruses could be inactivated by microwaves, and to try and determine what exact kill mechanism is responsible for this effect, AFRL constructed an apparatus that allows us to both propagate microwaves and droplets infected with the coronavirus surrogate. And so as the coronavirus travels, the microwaves are traveling with them, and so the exposure happens over a lengthened period of time. I'm not going to go into too much detail on that, but I will highlight a paper that we've put out that's publicly available that goes into great detail of how that system was constructed. So now to talk about my contribution to this project. In April of last year, I received and started upgrading a gyromagnetic nonlinear transmission line, or NLTL. Gyromagnetic NLTLs are very desirable for this application for a couple of reasons. First, they're solid state, which means that they don't produce any ionizing radiation that is common to many other kinds of high power microwave systems. You can see on the right-hand side, there's a picture of me in my scrubs, and I'm standing right next to it while it's operating without any hazard to me, to my health. The system is also a very compact one. You can see on the right-hand side that it's mounted on a very small cart that can be wheeled around hallways and rooms. And this system hasn't even been optimized for compactness yet. In my opinion, we can make it much smaller if that were desirable. And then finally, the system is also a very high peak power system, which allows us to probe the electromechanical kill mechanism. So that was very important to our research to kind of probe that mechanism. I also, as a part of my work to get this system ready and improved to the best that I could, I increased the operation frequency to about 4 or 4.25 gigahertz to optimize the virus interaction. Others had done some research to show, some modeling and simulation to show that higher frequencies coupled to the virus is better. And so we should get a much stronger reaction that breaks apart the virus. We hope that this would be more efficient. Also, as a part of my work, I increased the output power by a factor of 40. I increased the repetition rate by a factor of 60. And I increased the operation duration from minutes to hours. So this was how long we could run the system before it started to overheat and we had to shut it down. And finally, I improved the reliability of this system. When we first received it, we were getting breakdowns about once a minute or so. And this really impacted the repeatability and the quality of the output. But after I had improved the insulation, I changed it out a little bit and made some improvements. We were able to operate the system for hours without ever having any evidence of breakdown. So it was very successful. So we've been testing this system for the last year or so, and we're still collecting data on it. But now I'm going to pivot to the impact that the SMART Scholarship has had on my life and on my career. I enjoy my work with the DoD much more than any other work that I've done, and I've been performing research since 2007. And SMART connected me right to it. I think that if I hadn't been awarded this scholarship, that I wouldn't have considered a career in the DoD. I didn't know what they did. I didn't know what I could do with them. I didn't know how the job would be. But SMART allowed me to investigate that through internships, and they also guaranteed me a job here. And for that, I'm very grateful. I think it's been a great thing for me and for my life. I also think that this job is very special. As a part of my duties, I've gotten to travel to Australia and meet with researchers there and start collaborations with them. And through my work, I impact international relations almost every day, just by working with them and establishing those relationships. And I don't think that that's something that I could really do if I had pursued a different career. If I had ended up in industry, or if I had ended up pursuing the academic route to become a professor, I don't think that my work would be having an international impact so early in my career. It's something that I very much enjoy, and I'm very grateful to have the opportunity to do. In the last couple of years, I've won some awards. I've been very fortunate. Last year was very good for me and my team. We won the Director's Cup Team Award. That's at the directorate level. The S&T Achievement Team Award, also at the directorate level. The AFRL Innovation Team Award, and that's at the AFRL level. And in 2019, I won the International Outreach Individual Award. For leadership positions, I've held a couple. I'm currently the Deputy PI for the CKMA project, which is a major HPM system. The EBSEAM project, which is a large charged particle beam project. And then finally, I'm the Division Outreach Lead to Australia. I've also had a couple publications, either published or in the process of being published. The first I'll point out is the Hoff et al. Paper at the top there. That one has much more detail on our exposure apparatus to test the virus and the microwave interaction. So if you're interested in that, I encourage you to check out that paper. There's a lot more detail in there. But I've also published, I'm in the process of publishing 2 other papers that are related to this. So if you're interested, I encourage you to check them out. So with that, I want to thank you for your time, and I really appreciate your attention.
Thank you, Daniel. Our final presenter will be Sarah Hager, and her topic will be Shift Left to Deliver Warfighting Capabilities.
Hello, everyone, and thank you for coming to my talk today. My name is Sarah Hager. I'm currently a software engineer working at Kessel Run Labs in Hanscom Air Force Base in Massachusetts. It's formerly known as Detachment 12. I came to Kessel Run through my service commitment with the SMART program after completing my master's in computer science at Northeastern University. Today, I'm excited to talk to you about shifting left to deliver warfighting capabilities securely and reliably to air operations centers around the world. Kessel Run's mission is to deliver combat capability that can sense and respond to conflict in any domain, anytime, and anywhere. We harness agile and lean product development along with extreme programming to get software out to warfighters faster and better. If you're not sure what those terms are, no worries. I'll dive into what those mean in just a moment. There are several examples of other organizations using similar software development methods. We have Kessel Run in the Air Force, Section 31 in the Space Force, and Futures Command in the Army, just to name a few. So you might be wondering, how do we accomplish this mission effectively? So we have a couple goals. We want to reduce our batch size using continuous authority to operate, decrease product risk by releasing capability to users in increments, and limit the cost of delay. What does this mean? What does batch size mean? Oftentimes, the Air Force or other organizations release software updates to users perhaps once per year or even less frequently. We utilize a continuous ATO, authority to operate, to release more frequently, sometimes even weekly. We can decrease the product risk by releasing software updates in smaller chunks that allow us to iterate quickly given user feedback. This helps us to limit the cost of delay rather than release an update that does not meet user needs, either because the requirements were not properly defined or understood, or because the user needs changed. We're able to release quickly and we can pivot development as needed, thus reducing the cost of delay. Here's an example of cost of delay. Software built over 5 years on requirements. It's released after 5 years to the user. By the time the software is released, the technology is out of date and perhaps does not meet some specific user needs. So that's 5 years of development lost. So we want to reduce that cost of delay. There are some challenges with this. We work with systems that are highly distributed, connecting people, systems, and facilities to best enable our warfighters is challenging. Our warfighters win by having tools that are highly integrated, eliminating manual processes and siloed systems. We're able to overcome these complex problem spaces with iterative research and experimentation directly with our users. The tricky part of this is that our users have important jobs, so we must respect their time and be as minimally intrusive as possible while learning as much as we can from them. So we have a hypothesis here at Kessel Run that shift left enables us to deliver value faster. But what does shift left actually mean? It means that we shift risk earlier. If we can eliminate risk early, we can have more confidence in our iteratively developed products and get them out to users faster. We have a variety of techniques that we use to accomplish this. And the ones that you see on the screen here, test-driven development, pair programming, continuous integration, continuous development, iteration, and the following values are all elements of extreme programming that we use at Kessel Run. So TDD, test-driven development, ensures software reliability by designing automated tests first. Don't leave reliability to chance. And then pair programming, we use this to speed up our review cycle by using peer review. Rather than weekly or bi-weekly code review, it enables us to continuously deliver code and respond to issues quickly. And with CI/CD, we automate security. This is huge. We ensure the integrity of our systems by continuously developing with pair programming and continuously delivering with automated security pipelines. We can continuously push out updates to our software systems with confidence. And iteration. We want to be sure we're building the right thing. Quick cycles and shifting reliability and integrity left lets us respond quickly to user needs. And these values, communication, simplicity, feedback, courage, and respect, these are values that we live by. A culture of continuous feedback and respect enables us to trust each other to build the right thing with minimal waste. So how did this work out? What were the results of our hypothesis, and did we achieve what we were hoping to? So there's two major things that I've had the opportunity to work on in my time at Kessel Run. First was a greenfield application that was proven to reduce warfighters' reliance on PowerPoint in only 10 months. This helped us prove the value of the software product and eliminated the cost of delay. The second was a integrated application suite. We successfully released the Kratos suite, which enables integrated air operations planning. The 609th AOC commander said, this release was the biggest systems advancement the AOC has made since it first started using TBMCS in the 1990s. And Kessel Run was able to accomplish this in only 4 years. This is a huge proof of concept in applying iterative agile or lean product development in combination with extreme programming techniques like TDD, pair programming, CI/CD. I'm really excited to see other armed forces branches adopting similar principles. These techniques enable us to directly make good on our mission, delivering combat capability that can sense, respond to any situation, anywhere. I'm so proud of the work we've done to support our warfighters. I'd like to wrap up by covering a few of my achievements and highlights during my time at Kessel Run. I would say the most rewarding was working on the first continuous ATO in the DoD that led us to create the Kratos suite of applications. And I was really honored to serve on the core team building the Kratos suite as well. In addition, I got to exercise my leadership skills as tech lead for a greenfield application, the one I mentioned just before. And one of the most fun things I was able to do is build Castle Wren's engineering practice team. It was a working group team aimed at upskilling engineers in our organization, whether that was test-driven development, CI/CD, or pair programming. And I was additionally honored to receive 4 quarterly awards for technical excellence and engineering practice. I would be really remiss if I also didn't mention the fun things and unique opportunities I got to do. So one, of course, is the real mission impact, particularly during my LNO liaison officer rotation to an AOC in Qatar. That was definitely a highlight, to really work with our users and see the real life impact of our daily work. And of course, meeting a 4-star general and getting to pair programming with him was super fun and really inspiring to see support from leadership at the highest levels for innovation and advancement in technology. And with that, thank you so much for listening. I hope you enjoy the rest of your day. Thank you very much.
Thank you, Sarah. Ladies and gentlemen, at this point, if you could please navigate back to the agenda and click on the Q&A session, that will give you a Zoom link. Please follow that to get into our live question and answer session with our speakers.